All right. This is the third video on section 16.7 about the surface integral. And let's remember the stuff we did in the previous video, which is about the orientation of surfaces. So suppose you are given a parametric surface of UV, and then there are basically two orientations. Each of them is represented by the cross product like those, namely one of the orientation is this one, and the other is this one. You switch U and V, and indeed, if you compute a cross product like this, what you get is the vector perpendicular to the surface at each point. So remember, if you compute this and this, those are tangent to the surface at each point. So that means those two vectors span the tangent plane. So if you compute the cross product, what you get is a vector perpendicular to the tangent plane. So that means this vector at each point on the surface is a perpendicular to the surface, normal vector to the surface. And of course, if you switch the order of multiplication, where you switch U and V, what you get is the vector opposite to it. And then in this picture, basically, this represents upward orientation. And in this picture, this represents a downward orientation. Okay, then now with this said, in this video, I'm going to introduce the concept of surface integrals of vector fields. So this is actually the last kind of integral we cover in this course, surface integrals. Of a vector fields. Here's a question. Given a parametric surface, so given a surface as parameterized by I of UV, and then let's assume that our orientation is given by this direction, RU cross RV. So it's an oriented surface whose orientation is given in this way. And assume we are given, so also we are given a vector field f of x, y, z, vector field in R3, whose x component is p, y component is q, and z component is r. So p, q, r are functions of x, y, z. Then now, so pictorially, here is a picture. So we have the parametric surface, so UV plane gets mapped to, under R, some surface. Okay, then, so this is our surface S, so this is our UV. Okay, then now, then we have a vector field, so that means we have, let's think this way. Suppose XYZ space is, inside the ocean or swimming pool, and the water is flowing, and then vector field F represents flow, namely the flow of water. So water is flowing. So that means certain amount of flow goes through the surface at each point in the direction represented by the vector field F. So a bunch of those arrows are our F. Okay. Then now, suppose we look at some finite region, some bounded region on the UV plane. Let's call it D as usual. So then the corresponding region on the surface is some finite region on the surface. And let's call this S. Then now, the question is this. Suppose our vector field F represents, to be more precise, the amount of flow or mass of water per area. This represents the amount of flow. Or mass of flow, if you like. Per area. Then now, the question is this. Compute the total amount of flow going through this portion of the surface, S. And then this total amount of flow is often called flux. Okay. So now, here's the answer. Let me write down picture again. So we have our surfaces, and then we have this finite region on the surface. And this is our S. This is our S. And then, as usual, let's look at a small patch on the surface. And this has the area ds. So ds is the area of this small patch. And then first let's compute the total amount of flow going through ds instead of the entire S. To see it, let's just magnify this. Magnify this picture. And then this patch is more or less approximated as parallelogram like this. And then now, suppose, so this is the area of this patch. Okay, the area of this patch is equal to ds. And then now, let's look at a point in the patch, that's xyz, in the middle point of patch xyz. And then, suppose at this point, the flow, well, vector f is moving this way. There is no guarantee that the flow f is perpendicular to the patch or anything, just some random direction. Like this. Okay. Then now, so that means we are looking at the total amount of flow going through this patch, but the flow might not be going through the patch perpendicularly to the patch. Like it might have some direction like this. So that means the actual contribution of this flow F through this patch, or namely the contribution to the flux, is only this component which is perpendicular to the patch. Namely, suppose we put little n. N is the vector perpendicular to the patch. And then only the component in this direction, the vector perpendicular to the patch, contributes to the flux. So here, n is the normal vector to the patch with magnitude 1. We choose unit normal vector. Let's say n is a unit normal vector. Remember, unit vector means vector with magnitude 1. And then this vector here, this component here is the actual contribution. To the flux. And then let's call this angle theta. This is angle theta. So let's compute the actual contribution. The actual contribution to the flux is given by, well, it's a scalar, but essentially cosine of the magnitude of f. The magnitude of f, x, y, z, and the cosine theta of that. But what is this? This one is actually written as times, since the magnitude of n is 1, it's a unit vector. Unit vector means magnitude 1. This is written as cosine theta. And that is x, y, z dot n. So that's the actual contribution to the flux to this patch with area ds. So that means the flux, so therefore the flux through ds is equal to f of x, y, z dot n times ds, because this is our the flow per area, the amount of flow per area, and this is the area. Then now, as just a notation, this is written as f dot ds. Okay, this is a notation. So we call this portion ds. This is just a notation. Okay, so therefore, the total amount of flow going through the entire surface, namely flux through the surface S, is given by double integrating this all over S. And of course, this is written as f dot n ds. But what's ds now? Okay, even if you look at this, you can't really compute the actual flux. You want to express everything in terms of parameters u and v so that you can actually do the calculation. So here, let's recall, we have already seen this indeed. Let's recall the area of this small patch was written as this quantity, right? du dv. Well, maybe dA, I should say dA, where dA is du dv. And this vector n is what? Well, vector n is indeed this one, okay, divided, but this might not be a unit vector, might not have magnitude 1, so we divide it by its own magnitude, like this. And here, now here comes the issue of orientation. So we are assuming that the orientation of our surface is in this order, Ru cross Rv. So therefore, we have to choose Ru cross Rv instead of the other way around. And that's the flux in the direction of the orientation, to be precise. Right. Okay, so then therefore, so remember, so here at each point this, we have Ru, Rv, and then the vector perpendicular to it is the cross product, and we have to choose this consistently with the orientation. Choose actually n consistently with the orientation. Namely, we look at the contribution in the orientation. Choose the contribution to the flux in the same direction as the orientation of the surface. That's the idea. So that's why you have to choose this one. If the orientation is given the other way around, you have to choose the other way around. Anyhow, so therefore, let me just wrap this up first. So therefore, the flux is more concretely given as surface integral. And then now f, but f is in terms of x, y, z, but we want to express everything in terms of u and v. So you plug in the parameterization of the surface to the vector field we integrate, and then dot ds, but ds is n times ds. But what's n? N is this. So this is u cross divided by v, and then times ds, but ds is written this way, times dA, what dA is du dv. So therefore, we can cancel. And dA. So since this is a dot product of two vectors with variables u and v, this entire thing is a scalar. So this is a scalar valued function with variables u and v, and then you just double integrate over, actually not s, sorry. This is d. This is d. Okay, then where, let me just emphasize what this is. This means where f of r of uv is indeed f, but for x component, well, for the variable x, we plug in the x component of the parameterization, and y is yuv, and z is zuv. And then this integral is called the vector surface integral, or simply just flux. This is called the vector surface integral of f, or you may call it flux, through the surface S. Okay. But let's just work out some examples. Example. Compute surface integral f dot ds, where our vector field f, or f of xyz, is yxz, and S is z is equal to 1 minus x squared minus y squared, with z is bigger than or equal to 0. And the orientation is inward. Okay, so what is this? Well, first of all, it is helpful to visualize this. What is this? Remember, we have seen this kind of surface before. If we didn't have y, namely if you set y to be 0, that gives you the projection of the surface on the xz plane. And the xz plane, this is a parabola with vertex 1. And then if you do the same thing by switching x and y, what you get is the same picture on the yz plane. So this is actually rotated parabola. Z is equal to 1 minus x squared. It's a rotated parabola or paraboloid, opening downward with vertex 1. So this is pictorially x, y, z, like this. Okay, and this surface is not closed, by the way. We don't include the bottom cap. Okay. Open surface. And the orientation is downward. So downward orientation. So those bunch of arrows represents orientation. So how should we do this? Well, basically for surface integral of vector field, there are 3 steps. Okay, it's always like this. There are 3 steps. Step number 1. First thing to do is parameterize the surface. This is the same even for the surface integral of a scalar field. Remember, we have done this surface integral of a scalar field. And even for that, the key point is parameterization of the surface. And the same here, we parameterize the surface S. Like how? Well, like this. In this case, since our surface is given in this way, we could choose u is equal to x and v is equal to y. Namely, we can use x and y as parameters for the surface. So this is r of x, y. And then x is x, y is y, so to speak. And then z is this. 1 minus x squared minus y squared k. So this is the canonical way of parameterizing the surface. But we have to work out the domain for the parameterization. And as this says, z is bigger than or equal to 0. So this means we have to look at 1 minus x squared minus y squared is bigger than or equal to 0. And that's the same as saying x squared plus y squared is less than 1. Indeed, as you could tell, this is on the xy plane. The disk with radius 1, that's this bottom portion, right? That this bottom disk is the region where x and y can move around. But anyhow, more pictorially, by using the picture we have been using, we have xy plane and the domain D, the region D, this is D, is a disk with radius 1. And then by parameterization R, what we get is this portion of paraboloid. Okay, so that's a parameterization. And of course, just for your answer, by the way, you don't really have to write it down. This is something you should keep in your head. Anyhow, so that's step number 1. And step 2, compute the vector that gives the orientation. In this case, Rx and Ry. Well, what's Rx? You differentiate this with x, you get 1i, just I, plus if you differentiate y with y with x, you get 0, so 0j, plus now if you differentiate the last term, you get a negative 2x. Okay. And similarly, if you compute this, you get 0i plus j minus 2yk. So, now we can compute the cross product. And you do ijk 1, 0, negative 2x, 0, 1, minus 2y. And then if you work this out, you get 2xi plus 2yj plus k. Okay, then now we're sort of done with this, but actually we have to check the orientation of this to compute the surface integral vector field. And if the orientation given in the problem is not the same as the orientation given by this, we have to choose the other orientation. So to check the orientation. Of r of x cross r of y. Well, to do this, remember, what we have to do is to pick up a test point. So to speak. Test point on the surface. It doesn't matter where, but it's usually it's easy to pick up some easy point. Like in this case, the top of the mountain. Or let me just copy it here. Let's pick up this point. So this point is 0, 0, 1, meaning that when x is 1, x is 0, y is 0, of course. Then now, what's this? What this is, so at 0, 0, 1, namely x 0, y 0, the vector here evaluated 0, 0 is what? You plug in 0, 0, 0i plus 0j plus k. So this is just a k, vector k. But what's vector k? As a vector, this is 0, 0, 1, of course. And that's a vector pointing upward with no x component, y component. So vector k is this vector. Okay, this is our vector k. So that means those vectors given by this vector, when x, y go through in this region, are vectors pointing outside or outward orientation. Okay, so therefore, this one gives outward or upward, whichever you like, whichever language you prefer, outward orientation. Well, you may call it upward if you like. Okay, but now let's look at the problem. The problem says the orientation is inward, namely orientations are those. The orientation is represented by those vectors. So we need to choose the other way around. We need to choose y cross rx, namely that's negative rx cross ry, and that's just negative of this. Negative two xi, negative 2yj, negative k. Okay, so that's step number 2. Okay, step number 1, parameterize the surface. And step number 2, compute the orientation, the vector that gives the orientation, and make sure that that is consistent with the orientation given in the problem. And then finally, step 3, plug in everything to the formula. Plug in everything to the formula. So, like how? Like this. So the formula says f dot ds, and that is equal to double integral of f of, you plug in the parameterization to the vector field you integrate, dot ryrx. Remember, we use this one. So we have this here, and dx dy. And remember, our f or f of xyz is given as yxz. Okay, that's how it's given. And our parameterization r of xy was x y xi plus yj plus 1 minus x squared minus y squared k, right? So this means what? We have to plug in this to this, meaning that we have to plug in, we have to set y is y, x is, that's fine. Then now we have to set this z to be here. So this is double integral by using bracket notation. Y is y, x is x, and z is this guy. Squared dot, let me just erase it. This one. By using bracket notation, this is negative 2x. I'm switching the notation between the bracket notation and the IJK notation. I believe you guys are already used to those two notations by now. So it's like this. This guy is here. So this guy is here. And this guy here is this second vector here. Let's see what it is. All right. And then you compute the dot product. And you get negative 2xy, negative 2xy again, negative 1 plus x squared. I'm sorry, this is negative. Plus y squared dx dy. But what was d? Where d was, remember, d was just a disk with radius 1. Okay. So all you have to do is just work this out, compute this double integral. And then I'm not going to work out the detail. You can just simplify this as, by the way, minus 4xy minus 1 plus x squared plus y squared and dx dy. So since it's over the disk, what you do is to use the polar coordinates as usual, namely x is r cosine theta, y is r sine theta, and then here this one, x squared plus y squared is always r squared. That's part of the formulas for the polar coordinates. And then since its entire disk r is between 0 and 1, and the theta is between 2 pi, and then finally xy is dx dy is r dr d theta. Let's use the polar coordinates. And then if you work this out, eventually you are supposed to get negative pi over 2. This is just a little exercise for double integral using the polar coordinates. Okay, so that's a way to compute a surface integral of a vector field. And then now, essentially that's it for this section. But since surface integrals require more exercises, I'm going to work out a couple more examples of surface integrals of vector fields in the next video.